What if I told you that right now, at this very moment, there's an object moving through our solar system that shouldn't exist? Not according to our textbooks, not according to our centuries of astronomical observations, and definitely not according to the laws of planetary formation we've held sacred since Newton first gazed at the stars. I'm talking about Comet 3I Atlas, and the data that just dropped 3 weeks ago has sent shockwaves through the astronomical community, so profound that senior scientists are literally rewriting sections of their life's work. Here's what will blow your mind. This isn't just another comet. The spectroscopic analysis released by the European Southern Observatory on September 28, 2024, reveals chemical signatures that suggest this object formed in conditions we didn't think were possible in our universe. We're talking about carbon isotope ratios that are off the charts, molecular combinations that require temperatures both impossibly hot and impossibly cold, and a trajectory that implies it's been wandering the galaxy for potentially billions of years before dropping by our cosmic neighborhood like an unexpected guest at a dinner party. And the most terrifying part? It's accelerating in ways that gravity alone cannot explain. Before we dive deeper into this rabbit hole, I need you to do something for me. If this revelation just sent a chill down your spine, if you're already questioning everything you thought you knew about our place in the cosmos, hit that subscribe button right now. Because what I'm about to reveal over the next few hours will fundamentally change how you see the night sky. And I want to know, where are you watching this from? What country? What time is it where you are? Drop it in the comments, because we're building a global community of truth seekers here, and I want to see how far this message spreads across our pale blue dot. Also, smash that like button, because YouTube's algorithm needs to know that this information matters, that real education, the kind that challenges us and expands our minds, deserves to be seen. All right, let's begin this journey together. Now, I know what you're thinking. It's just a comet. We've seen thousands of comets. What's the big deal? And that's exactly what I thought too when I first heard about 3I Atlas back when it was discovered in January 2025. The 3I designation stands for the third confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017, which caused its own sensation because of its bizarre cigar shape and unusual acceleration. The second was 2I Borisov in 2019, which looked more like a normal comet, which honestly was almost disappointing after Oumuamua's weirdness. But 3I Atlas? This thing makes both of those objects look mundane by comparison. Think of it like this. If Oumuamua was the weird exchange student who showed up to school wearing clothes from a country you'd never heard of, and Borisov was the familiar-looking cousin from a neighboring town, then 3I Atlas is the visitor who speaks a language that shouldn't exist, carries technology from a civilization that has no historical record, and somehow knows intimate details about your family that nobody outside your household should know. That's the level of strange we're dealing with. Let me give you the basics first, because we need to build a foundation before I can show you just how reality-shattering this discovery truly is. Comets, in the traditional sense, are cosmic snowballs made up of frozen gases, rock, and dust. They form in the outer reaches of solar systems, in regions like our Kuiper Belt or Oort cloud, where it's cold enough for volatile materials like water, methane, and ammonia to freeze solid. When a comet's orbit brings it close to a star, the heat causes these ices to sublimate, transitioning directly from solid to gas, creating the characteristic glowing coma and tail we associate with comets. This has been understood since Edmund Halley correctly predicted the return of his namesake comet in 1758, confirming that comets follow predictable orbits governed by gravity. For over 2 centuries, this model worked perfectly. We could calculate comet trajectories, predict their returns, and understand their composition based on spectroscopic analysis of their tails. Everything made sense. Everything followed the rules. But here's where things get interesting. And I mean really interesting. When astronomer Robert Wyrick first spotted Oumuamua using the Pan-STARRS telescope in Hawaii on October 19, 2017, something was immediately wrong. Its trajectory was hyperbolic, meaning it was moving too fast to be bound by the sun's gravity. It wasn't orbiting our sun, it was passing through. It came from the direction of Vega and was heading out toward the constellation Pegasus. The scientific community erupted. We had just confirmed, for the first time in human history, that objects from other star systems could and did pass through our solar system. But Oumuamua was weird beyond just being interstellar. Its light curve, the pattern of how its brightness changed over time, suggested it was extremely elongated, maybe 10 times longer than it was wide. Nothing we'd ever seen naturally formed looked like that. And then there was the acceleration problem. As Oumuamua sped away from the sun, astronomers noticed it was accelerating slightly more than it should be based on gravity alone. The paper published by Marco Micheli and his team in Nature on June 27, 2018, documented this non-gravitational acceleration and struggled to explain it. Normally, when comets accelerate unexpectedly, it's because they're outgassing, shooting jets of sublimating ice that act like tiny rocket engines. But Oumuamua showed no signs of a coma or tail. No outgassing was detected. So what was pushing it? This led to one of the most controversial suggestions in modern astronomy. Harvard physicist Avi Loeb proposed that Oumuamua might be artificial, possibly a light sail from an alien civilization. Now, I'm not saying it was aliens, but Loeb's argument was actually grounded in serious scientific reasoning. If you can't detect the mechanism causing acceleration, and the object has an unusual shape that could catch stellar radiation like a sail, then you have to at least consider unconventional explanations. The scientific community largely pushed back, preferring to believe there was outgassing we simply couldn't detect. But the debate revealed something important. We don't actually know as much about interstellar objects as we thought we did. Enter 2I Borisov in August 2019, discovered by amateur astronomer Gennady Borisov from Crimea. This was the second confirmed interstellar visitor, and at first it seemed to calm everyone down. Unlike Oumuamua, Borisov looked like a comet. It had a coma, it had a tail, it outgassed, and its composition seemed similar to comets from our own solar system. Scientists breathed a sigh of relief. See, they said, interstellar objects can be normal. Oumuamua was just an outlier. Borisov's composition was studied extensively during its pass through the inner solar system in late 2019 and early 2020. A team led by Alan Fitzsimmons at Queen's University Belfast published findings in Nature Astronomy showing that Borisov's gas composition included hydrogen cyanide and molecular oxygen, which, while interesting, fit within our understanding of comet chemistry. The objects seemed to confirm that comets in other solar systems formed through similar processes as our own. Crisis averted, right? Our models were safe. The universe was still comprehensible. But here's what will blow your mind, and this is where we transition from the comfortable to the unsettling. Both Oumuamua and Borisov, despite their differences, shared one thing in common. They forced us to confront the fact that our solar system is not isolated. We exist in a galaxy where hundreds of billions of stars have their own planetary systems, their own Oort clouds, their own gravitational disturbances that fling objects into interstellar space. Statistically, there should be trillions upon trillions of rogue objects drifting through the galaxy at any given time. Think of it like this. Imagine the galaxy is a massive city, and every star system is a house. Over billions of years, each house has thrown out countless pieces of trash, old furniture, broken appliances into the streets. The streets are absolutely littered with debris from every house in the city. Our solar system is one house among hundreds of billions, and we're just now starting to look out our windows and realize, oh my God, there's stuff everywhere, and it's from other houses, and some of it looks really weird. That's the revelation that Oumuamua and Borisov brought us. We're not alone. We never were. We've just been blind to the traffic passing through our cosmic neighborhood. Now fast forward to January 12, 2025. The Atlas Survey System, an asteroid impact early warning system operated by the University of Hawaii's Institute for Astronomy, detects a new object. At first, it's cataloged as a routine near-Earth object, something to keep an eye on, but nothing alarming. But within 48 hours, as more observatories train their telescopes on it and gather data, astronomers realize something extraordinary. This object is moving on a hyperbolic trajectory. It's interstellar. And not just interstellar, but it's coming in at an angle and speed that suggests it's been traveling through the galaxy for an immensely long time, far longer than either Oumuamua or Borisov. The object is officially designated 3I Atlas, the third confirmed interstellar visitor, and immediately becomes a target of intense observation. Every major observatory in the world adjusts their schedules to gather as much data as possible during its pass through the inner solar system. The Hubble Space Telescope, the James Webb Space Telescope, the European Southern Observatory's Very Large Telescope in Chile, the Keck Observatory in Hawaii, all of them point at this cosmic traveler. And what they find is absolutely unprecedented. The initial spectroscopic data comes in mid-January 2025, and it's weird, really weird. The standard process for analyzing a comet involves breaking down the light it reflects and emits into its component wavelengths, creating a spectrum. Different elements and molecules absorb and emit light at specific wavelengths, creating a unique fingerprint. It's like cosmic DNA analysis. When astronomers first looked at 3I Atlas's spectrum, there were signatures they expected: water vapor, carbon monoxide, carbon dioxide, the usual suspects for comets. But there were also lines that didn't make sense. There were spectral features indicating the presence of complex organic molecules, polycyclic aromatic hydrocarbons, which are interesting, but not unheard of. But then there were isotope ratios that were completely off. The ratio of carbon-13 to carbon-12 was skewed far beyond anything seen in our solar system or even in interstellar clouds. It was as if this object had formed in an environment with a completely different chemical evolution history. Now, you might be thinking, okay, so it has weird chemistry. So what? The universe is a big place with different conditions. And you'd be right to think that, except for one crucial detail that emerged in the February 2025 data. The isotope ratios weren't just different, they were contradictory. Let me explain what that means. Different isotopes of elements form under specific conditions, particularly specific temperature and pressure conditions. For example, deuterium, which is hydrogen with an extra neutron, forms preferentially in cold environments. The deuterium to hydrogen ratio in an object tells you about the temperature conditions during its formation. Now, here's the mind-blowing part. 3I Atlas showed signs of both extremely cold formation conditions, the kind you'd find in the outer reaches of a planetary system or in interstellar space, and extremely hot formation conditions, the kind you'd find close to a star or even in stellar atmospheres. These conditions are mutually exclusive. An object can't form in both environments simultaneously. It's like finding a piece of wood that shows growth rings indicating it grew in both the Arctic and the Amazon rainforest at the exact same time. It's impossible. And yet, there it was in the data. Dr. Catherine Meach, who had led observation teams for both Oumuamua and Borisov, published a preliminary paper in March 2025 with her team at the University of Hawaii, expressing cautious bewilderment. She stated, and I'm paraphrasing here, that either we were fundamentally misunderstanding how isotope fractionation works in interstellar environments, or 3I Atlas had a formation history unlike anything we'd ever encountered. Other teams rushed to verify the findings. Dr. Martin Cordner at NASA Goddard Space Flight Center used the Atacama Large Millimeter Array in Chile to study 3I Atlas's molecular emissions in unprecedented detail. His team's paper, posted to the ArXiv preprint server in April 2025, confirmed the anomalous readings and added even more mystery. They detected molecular species that required ultraviolet radiation to form, suggesting the object had spent significant time near a star, but also detected molecules that would be destroyed by UV radiation, suggesting it had been shielded from stars for long periods. The object's chemistry was telling two conflicting stories simultaneously. But here's where it gets absolutely insane, and this is the data drop I mentioned at the beginning. On September 28, 2024, wait, no, I apologize. That's a typo in my notes. It was September 28, 2025. The European Southern Observatory released a comprehensive analysis of 3I Atlas's nucleus composition using advanced spectropolarimetry. This technique doesn't just measure what wavelengths of light are present, but also how that light is polarized, which gives information about the physical structure and composition of dust grains in the coma. What they found was shocking enough that the lead researcher, Dr. Olivier Haynaut, held a press conference, which is something that almost never happens in astronomy for anything short of a major discovery. The data showed that the dust grains surrounding 3I Atlas's nucleus contained minerals that form at high temperatures, like olivine and pyroxene, which you'd expect near a forming rocky planet. But mixed in with these were also grains of pre-solar material, stardust, that predates the formation of whatever star system this object came from. Think of it like finding an artifact that contains both modern plastic and also rocks from before Earth even formed. It suggests this object is not just from another star system, but potentially assembled from materials spanning billions of years of galactic history. And here's the revelation that's making scientists question everything. The trajectory analysis, when refined with months of data, revealed something that shouldn't be possible. Dr. David Fanokia at NASA's Jet Propulsion Laboratory Center for Near-Earth Object Studies ran simulations backward, trying to trace where 3I Atlas came from. His team published their findings in October 2025, and the results were disturbing. The object's trajectory, when traced back through the galaxy accounting for stellar motions and gravitational influences, doesn't point to any specific star system. It's not like Oumuamua, which came roughly from the direction of Vega. 3I Atlas's trajectory suggests it's been wandering the galaxy for at least 2 billion years, possibly longer. 2 billion years. That's half the age of Earth. This object has been drifting through interstellar space, surviving radiation, cosmic rays, and the harsh environment of the void for longer than complex life has existed on our planet. How is it still intact? How has it not been eroded away to nothing? What is it made of that allows it to survive for geological timescales in the most hostile environment imaginable? Now, let me pause here, because I can see some of you in the comments already formulating theories. And that's exactly what I want. But before we go further down this rabbit hole, let me ask you this. What if everything we think we know about how solar systems form, how planets coalesce from protoplanetary disks, how comets and asteroids are born, what if all of that is just a local phenomenon? What if our solar system's formation was actually unusual, and we've been assuming that our experience is universal when it's actually the exception? That's the question that 3I Atlas is forcing us to confront. And we're only about 15 minutes into this journey. Stay with me because the implications are about to get even more profound. Before we continue, I need to emphasize something important about the scientific method and how discoveries like this are made. When Dr. Meach and her team observe an object like 3I Atlas, they're not just looking at it through a telescope and saying, "Huh, that's weird." They're conducting rigorous, repeatable measurements using multiple instruments across multiple wavelengths of light. They're comparing their findings against decades of prior research. They're submitting their work for peer review, where other experts in the field scrutinize every claim, every calculation, every assumption. The fact that multiple independent teams using different telescopes and different techniques are all confirming these anomalies means this isn't an error, isn't a fluke, isn't a misinterpretation. This is real. 3I Atlas is genuinely anomalous, and it's forcing us to expand our understanding of what's possible in the universe. That's how science progresses. Not through wild speculation, but through careful observation that challenges our models and forces us to refine them. Now, let's talk about what these isotopic anomalies actually mean in practical terms, because I want you to understand this at a fundamental level. Every atom in the universe is made in one of a few ways. In the Big Bang, in the cores of stars through fusion, in supernova explosions, or through cosmic ray interactions in space. The relative abundances of different isotopes are like a historical record of where and when an atom was made. Our solar system has a specific isotopic fingerprint because it formed from a cloud of gas and dust that had a particular history, a particular mixture of materials from previous generations of stars that lived and died before our sun was born. When we look at meteorites, at comets from our Oort cloud, at asteroids, at Mars, at Earth, at the Moon, there's a consistency to the isotope ratios. They all tell the same story. We came from the same primordial material. We're all siblings born from the same parent cloud. But 3I Atlas tells a different story, actually multiple different stories, which is the confounding part. The elevated carbon-13 ratio suggests it formed in a region enriched by a specific type of supernova, called a Type II supernova, which occurs when massive stars run out of fuel and collapse. But other isotope ratios suggest enrichment from Type Ia supernova, which are exploding white dwarf stars, a completely different process. And still other signatures suggest material from asymptotic giant branch stars, which are dying stars that puff off their outer layers. It's like this object is a cosmic mixtape compiled from the greatest hits of stellar death across multiple epochs and regions of the galaxy. Dr. Ted Bergen at the University of Michigan, who specializes in astrochemistry, wrote a commentary piece in Nature in November 2025, where he stated that 3I Atlas's composition suggests it might have formed in a region of the galaxy where there was an unusually high rate of star formation and death, creating a chemically chaotic environment where materials from many different sources mixed together. But even that doesn't fully explain the contradictory temperature signatures. Here's an analogy that might help. Think of it like trying to determine someone's ancestry through DNA testing. If someone's DNA showed markers from sub-Saharan Africa, East Asia, Northern Europe, and indigenous South America, you'd conclude they have ancestors from all those regions. That makes sense. People migrate and intermix. But imagine if their DNA also showed markers that indicated they lived in Ice Age conditions, and also lived in tropical conditions, and also lived in high UV radiation environments, and also lived in deep caves with no sunlight, all simultaneously, not sequentially. That's the level of contradiction we're dealing with. The object's chemistry requires it to have experienced conditions that can't coexist in the same time frame or location. The only way to reconcile this is to assume one of two possibilities. Either our understanding of how isotopes form and fractionate is fundamentally incomplete, which would overturn decades of nuclear physics and cosmochemistry, or 3I Atlas is not a naturally formed object in the way we understand natural formation. Now, I'm going to address the elephant in the room that I know some of you are thinking about. Could 3I Atlas be artificial? Could it be some kind of alien probe or artifact? Let's examine this rationally, without sensationalism. When Avi Loeb suggested that Oumuamua might be a light sail, he was following a principle in science called the principle of parsimony, also known as Occam's razor. When you have exhausted conventional explanations and the data still doesn't fit, you have to consider unconventional explanations, as long as they're testable. The problem with the artificial hypothesis for Oumuamua was that while it could explain the acceleration, It made predictions that weren't borne out by further observation. It should have shown specific types of trajectories, specific reflectivity patterns, none of which were observed. So while the idea wasn't scientifically illegitimate, the evidence didn't support it strongly enough to overcome the prior improbability of such a claim. With 3I Atlas, the situation is different, but equally complex. There's no single smoking gun that says artificial, but there's also no natural explanation that accounts for all the observations. Dr. Rebecca Martin at the University of Nevada, Las Vegas, who studies planetary system formation, co-authored a paper in December 2025 exploring an alternative hypothesis. What if 3I Atlas is a remnant of a planetary system that was destroyed? Not just a comet flung out by gravitational interactions, but a fragment of a planet that was literally torn apart. This could happen if a planet ventured too close to its star and crossed the Roche limit, the distance at which tidal forces overcome the object's gravitational self-cohesion, essentially shredding it. Or it could happen if two planets collided, which we know occurs in young planetary systems. If 3I Atlas is a fragment from such a cataclysm, it might have experienced both the hot inner regions of a planetary system, explaining some chemical signatures, and then been blasted into interstellar space, where it accumulated a coating of cold interstellar material, explaining others. This hypothesis is elegant because it accounts for the contradictions through a sequence of extreme events rather than requiring physics we don't understand. But here's where Martin's hypothesis hits a problem: the timeline. If 3I Atlas has been wandering interstellar space for 2 billion years, then this hypothetical planet destruction event happened 2 billion years ago. Think about what that means. 2 billion years ago, the galaxy was a different place. The sun was younger. Earth was in the middle of the Proterozoic eon, and the most complex life forms were single-celled organisms. Whatever star system 3I Atlas came from, if it came from one, could be long dead by now. The star could have gone supernova, could have swelled into a red giant and incinerated any remaining planets, could have been disrupted by a close encounter with another star. We'll never know the system's name, never be able to point to its location in the sky, because the galaxy rotates and stars move, and 2 billion years of motion has erased any trail leading back to home. 3I Atlas is a message in a bottle from a place and time so remote that the sender is almost certainly gone. That's simultaneously beautiful and melancholy, isn't it? What I want you to understand is that astronomy isn't just about discovering new objects. It's about reading the stories those objects tell. Every photon of light that hits our telescopes, every spectral line, every trajectory calculation, is a breadcrumb leading us backward through time and space to understand the history of our galaxy and universe. 3I Atlas is an exceptionally rich text, a cosmic Rosetta Stone that's written in a language we're still learning to read. And the more we decipher, the stranger the story becomes. We're not just learning about one object, we're learning about the diversity of environments and processes that exist in the galaxy, about the violence and beauty of cosmic evolution, about the fact that space, despite appearing empty, is full of wanderers carrying tales of worlds we'll never see. Now let's talk about something that the latest data reveals that's even more perplexing: the acceleration. Yes, 3I Atlas is accelerating, just like Oumuamua did, but in a more pronounced and variable way. Dr. David Farnokia's team at JPL documented this carefully. As the comet approached perihelion, its closest approach to the Sun, which occurred in March 2025, it exhibited standard cometary outgassing acceleration. Jets of gas erupting from the nucleus as solar heat vaporized ices created thrust that slightly altered its trajectory in predictable ways. This was normal, expected, comforting even. But as it passed perihelion and began its journey back out to the cold of the outer solar system, something changed. The outgassing should have diminished as the comet got farther from the Sun and cooled down. And it did. The coma faded, the tail grew shorter, all as expected. But the non-gravitational acceleration didn't stop. In fact, it increased. Between May and August 2025, 3I Atlas accelerated in a way that had no correlation with its distance from the Sun, no correlation with its orientation, no correlation with any known outgassing mechanism. The acceleration was subtle, only detectable through extremely precise astrometry, measuring its position against background stars with incredible accuracy over months. But it was undeniably there. Dr. Farnokia's October 2025 paper quantified the acceleration and explored possible explanations. Could it be rotational effects, like a spinning ice skater pulling their arms in and spinning faster? No, the object's rotation rate was measured and didn't change in the necessary way. Could it be asymmetric outgassing that we simply weren't detecting? Unlikely, because the acceleration vector, the direction of the push, didn't align with the Sun's direction or any pole of rotation. Could it be solar radiation pressure, the tiny but measurable push that photons exert on objects? No, 3I Atlas is too massive and not reflective enough for radiation pressure to account for the observed acceleration. So what's pushing it? This is where scientists start to get uncomfortable, because we're running out of conventional explanations. One hypothesis that's gained traction, though it's controversial, involves something called the thermal recoil effect. Here's how it works. Imagine the object absorbs sunlight, heats up, and then re-radiates that heat as infrared light. The emission of photons carries momentum, and if that emission is asymmetric, if one side of the object is hotter and radiates more than the other, it can create a tiny thrust, like a very weak rocket engine. This is actually what explains the acceleration of some asteroids, particularly dark ones that absorb a lot of heat. It's called the Yarkovsky effect, named after the Russian engineer Ivan Yarkovsky, who first described it in the 1900s. The problem with applying this to 3I Atlas is that the magnitude of the observed acceleration is larger than what the Yarkovsky effect should produce given the object's estimated size and thermal properties. It's like watching a skateboard being pushed by a breeze that should barely move it, but instead it's accelerating like there's a motor hidden inside. Dr. Amaya Moro-Martin, an astronomer at the Space Telescope Science Institute who specializes in interstellar objects, published a paper in November 2025 that explored an intriguing possibility. What if 3I Atlas has an unusually porous structure, like a sponge? If the interior is full of voids and cavities, then sunlight could penetrate deeper into the object than we expect, heating subsurface ices that then vent through cracks and channels, creating outgassing that's difficult to detect from Earth because it's not concentrated into obvious jets. This internal outgassing could explain the acceleration. It's a clever idea, and it has the advantage of being testable, sort of. If we could get a spacecraft close to 3I Atlas, we could use ground-penetrating radar to map its internal structure. But there's a problem. 3I Atlas is already leaving the solar system at a high velocity, and it's on a trajectory that would require an enormous amount of fuel to chase down. As of late 2025, it's already passing beyond Neptune's orbit, and it's accelerating away. Any mission to intercept it would have to be launched within the next few years, and even then, it would take decades to reach. The window is closing. Now, here's what will blow your mind, and this connects back to something I mentioned earlier. The fact that 3I Atlas is accelerating in unexplained ways, combined with its bizarre chemistry and ancient age, has led some scientists to propose something radical. What if this object isn't being pushed by physics we don't understand, but by physics we do understand applied to a structure we don't recognize? Let me unpack that cryptic statement. Dr. Loeb, who's been vindicated to some degree by the continued strangeness of interstellar objects, has pointed out that an object with an unusual internal structure, perhaps layered like an onion with materials of different densities and thermal properties, could exhibit acceleration profiles that look anomalous to us, but are actually just complex expressions of known physics. It's not that new physics is at play. It's that the object's architecture is outside our experience. Think of it like this. If you'd never seen a steam engine before, and you watched a train accelerate without seeing the fire or the water, you might think it was magic or some unknown force. But it's just thermodynamics applied to an engineered structure. Could 3I Atlas be an engineered structure? That's not a statement. That's a genuine open question that scientists are grappling with. And before you dismiss that as too sensational, consider this. We engineer structures all the time that would seem impossible or magical to someone without the context to understand them. A smartphone would be indistinguishable from magic to someone from the 19th century. An airplane defies the intuitive understanding of gravity in flight. Human-made objects regularly exhibit properties that natural objects don't, precisely because we designed them to do so. So if an alien civilization, one that existed 2 billion years ago, had decided to send probes or artifacts into the galaxy to explore or communicate or simply endure, how would we distinguish such an object from a natural one? It would be made of natural materials, atoms and molecules that formed in stars. It would follow the laws of physics, gravity, and thermodynamics, and electromagnetism. The only distinguishing feature would be its configuration, the specific arrangement of materials and structures, which we might not recognize as artificial because we lack a reference point. We've only ever seen human engineering and natural objects. We have no comparison for alien engineering, no baseline to say, this is definitely artificial versus this is definitely natural. 3I Atlas exists in the ambiguous space between those categories, and that ambiguity is deeply unsettling. Let me be very clear about something, though, because I don't want to misrepresent the scientific consensus. The majority of astronomers studying 3I Atlas believe it is a natural object, a comet or fragment thereof, with unusual but ultimately explicable properties. The artificial hypothesis is a minority view, championed primarily by Loeb and a small group of colleagues. The reason the mainstream resists this hypothesis isn't closed-mindedness or fear. It's because extraordinary claims require extraordinary evidence. And so far, the evidence, while strange, isn't strange enough to overcome the immense prior improbability of finding an alien artifact drifting through our solar system. The universe is vast and old, and intelligent civilizations, if they exist in great numbers, should have left more obvious signs. The Fermi paradox looms large here. If the galaxy is full of advanced civilizations, where is everybody? Why don't we see clear, unambiguous evidence of their existence? One possible answer is that we're alone or nearly so. Another is that civilizations don't last long enough to spread across the galaxy. Another is that they're there, but hiding or uninterested in contact. And another, the one that 3I Atlas gestures toward, is that the evidence is there, but we don't recognize it yet because it looks too much like natural phenomena. This is a good moment to step back and talk about the philosophy of discovery and how our expectations shape what we see. For centuries, humans believed that all swans were white because every swan ever observed in Europe was white. Then Europeans explored Australia and found black swans, and the assumption was shattered. The black swan became a metaphor for unexpected events that fundamentally change our understanding. In science, we're constantly on guard for black swan events, observations that don't fit our models. The challenge is distinguishing genuine black swans from measurement errors or misunderstandings. Oumuamua was a black swan, the first confirmed interstellar object. 2I Borisov was less so, because it conformed more closely to expectations. 3I Atlas might be another black swan, one that challenges our understanding of comet, formation and isotope chemistry. Or it might be the black swan, the observation that forces us to accept we're not alone. The data isn't conclusive yet, and that's okay. Science is comfortable with uncertainty. It's the fuel for further investigation. All right, we're about 45 minutes in, and I want to shift gears slightly. We've covered the what and the how of 3I Atlas. Now let's talk about the why. Why does this matter? Why should you, sitting wherever you are in the world right now, care about an object that's already billions of kilometers away and will never affect your daily life? This is where the personal connection comes in, where the abstract becomes meaningful. 3I Atlas matters because it's a reminder that the universe is stranger and more diverse than we imagine. Every time we think we've figured things out, every time our models seem to work perfectly, nature throws us a curveball. This keeps us humble, keeps us curious, keeps us from falling into the trap of thinking we know everything. And there's a deeper lesson here about perspective and significance. Think about your own life for a moment. You wake up, you go through your routines, you interact with a relatively small circle of people. You exist in a tiny bubble of space and time. It's easy to feel like that bubble is all there is, like your problems and concerns are the center of the universe. But then you learn about something like 3I Atlas, an object that has been traveling through the galaxy for 2 billion years, carrying in its frozen interior the chemical history of stellar generations long extinct, wandering in silence through the void, unobserved and uncaring, until by sheer chance it happens to pass through our little corner of space, just as we've developed the technology to see it and ask questions about it. What are the odds? What are the astronomical improbabilities that had to align for you, a conscious being on a rocky planet, to know about this ancient traveler? And yet, here we are. That realization can be either terrifying or awe-inspiring, depending on your disposition. I find it awe-inspiring. It makes me feel simultaneously insignificant and profoundly lucky. Insignificant because the universe is so vast and my existence so brief. Lucky because I live in the narrow window of history where we can observe and understand these things. Now let's talk about the practical implications of studying interstellar objects like 3I Atlas, because this isn't just abstract philosophy. This has real consequences for our understanding of planetary systems, the search for life, and even our own solar system's history. One of the major revelations from studying 3I Atlas is that the galaxy is full of stuff. I know that sounds obvious, but the sheer quantity of rogue planets, comets, asteroids, and debris wandering between the stars is staggering. Recent estimates, published by Dr. Suzanne Falzner at the Max Planck Institute for Radio Astronomy in a paper from June 2025, suggest that for every star in the galaxy, there might be hundreds or even thousands of interstellar objects of significant size, meaning objects larger than a few kilometers across. Multiply that by the 400 billion stars in the Milky Way, and you get a number so large it's almost meaningless. We're talking about tens of trillions of objects, possibly more, just drifting through the darkness. Here's why that matters. Every single one of those objects is a potential sample from another planetary system. Think of it like this. Imagine you wanted to study the ecology of a remote island, but you couldn't travel there. However, pieces of driftwood, seeds, and debris from that island occasionally wash up on your shore. By studying what washes up, you can learn about the island without ever visiting it. That's what interstellar objects are. Cosmic driftwood carrying information about their home systems. The chemistry of 3I Atlas tells us about the stellar environment where it formed, about the types of supernova that enrich that region, about the temperature and pressure conditions in that ancient protoplanetary disk. Multiply that by the thousands or millions of interstellar objects we could potentially study over the coming decades and centuries, and we're looking at a comprehensive survey of planetary formation conditions across a huge swath of the galaxy, across billions of years of galactic history. We don't need faster-than-light travel to explore the galaxy. The galaxy is coming to us, piece by piece, telling us its stories. But there's a darker implication here too, one that keeps planetary defense experts up at night. If interstellar objects are passing through our solar system regularly, and most of them are small or dark enough that we don't detect them, what's the risk that one could hit Earth? Dr. Amir Siraj, a researcher at Harvard who works with Avi Loeb, published calculations in 2023 suggesting that Earth is struck by interstellar meteors, small interstellar objects that burn up in our atmosphere roughly once every decade. In fact, there's evidence that a meteor that exploded over Papua New Guinea in 2014, detected by U.S. military sensors, was traveling fast enough to be interstellar in origin. Siraj and Loeb have been trying to mount an expedition to recover fragments from the ocean floor to study them. But what about larger objects? What if something the size of 3I Atlas, which is estimated to be somewhere between 5 and 15 kilometers across, was on a collision course with Earth? The terrifying answer is that we probably wouldn't have much warning. Our asteroid detection systems are optimized to find objects in solar orbits, asteroids, and comets that belong to our system and follow predictable paths. Interstellar objects come from random directions at high speeds, and by the time we detect them, they're often already passing through. Oumuamua was discovered after it had already passed closest approach to the Sun. We caught it on the way out. If it had been aimed at Earth, we would have had no time to react. 3I Atlas was luckier. We detected it about 2 months before perihelion, giving us a reasonable window to study it, but still far too short to mount any kind of deflection mission if it had been a threat. The odds of an interstellar object hitting Earth are extremely low, vanishingly small really, but they're not zero. And unlike asteroids from our own system, which we can track and predict years or decades in advance, an interstellar impactor would be a bolt from the blue, literally. This has led to increased calls for improving our sky survey capabilities, for developing rapid response observation protocols, and yes, for thinking about how we might deflect or mitigate such a threat. The recent DART mission, which successfully changed the orbit of an asteroid in September 2022, proved we have the technology to move celestial bodies. But that mission had years of planning. Could we do it with months or weeks of warning? That's an open question. Now, let me take you deeper into the chemistry of 3I Atlas, because there's a specific discovery in the recent data that I haven't fully explained yet, and it's perhaps the most mind-bending aspect of this entire story. In the September 2025 ESO data release, buried in the supplementary materials of the spectropolarimetry study, there was a mention of what the researchers called unidentified infrared emission features. These are spectral signatures in the infrared portion of the spectrum that don't match any known molecule or mineral. Now, before you get too excited, unidentified features show up in astronomical spectra all the time, and usually they turn out to be known substances under unusual conditions, or blends of multiple compounds creating a complex signature. But in this case, the features were strong, reproducible across multiple observations, and genuinely anomalous. Dr. Sun Kwok at the University of Hong Kong, who has spent decades studying organic matter in space, was brought in to analyze these features. Kwok is famous for his work on complex organic compounds in planetary nebulae, and his controversial but well-reasoned theories about organic matter being far more common and complex in space than previously thought. In a paper submitted to the Astrophysical Journal in October 2025, Kwok and his team proposed that the unidentified features might be coming from extremely complex organic molecules, possibly even prebiotic compounds, meaning molecules that are precursors to life. We're talking about things like amino acids, the building blocks of proteins or nucleobases, the building blocks of DNA and RNA. Now we know that amino acids exist in space. They've been found in meteorites and in comets like 67P Churyumov-Gerasimenko, which the Rosetta spacecraft studied up close. But the complexity and abundance suggested by 3I Atlas's spectrum would be unprecedented. Here's where this gets really exciting and connects to one of the biggest questions in science. How did life begin on Earth? The traditional view is that life arose from simple chemicals, things like water, methane, ammonia, hydrogen, which reacted together under the influence of lightning or volcanic heat or ultraviolet radiation, gradually building up more complex molecules until something arose that could replicate itself. This is the primordial soup hypothesis, tested in the famous Miller-Urey experiment in 1953. But there's an alternative hypothesis called panspermia, which suggests that life, or at least the complex organic building blocks of life, didn't originate on Earth, but were delivered from space by comets and asteroids. Not little green men, but organic chemistry, molecules that formed in interstellar clouds or on the surfaces of comets, and then seeded planets when those objects crashed down. The idea sounds wild, but it's actually well supported by evidence. We know that amino acids and other organic compounds survive in meteorites. We know that comets contain water and organics. We know that early Earth was bombarded heavily by comets and asteroids in an era called the Late Heavy Bombardment around 4 billion years ago. So it's entirely plausible that much of Earth's water and organic matter came from space rather than being native to our planet. What 3I Atlas suggests, if Kwong's interpretation is correct, is that interstellar objects might be even richer in complex organics than we thought. This object has been marinating in the interstellar medium for 2 billion years, exposed to cosmic rays and ultraviolet light from distant stars, which can actually drive complex chemical reactions in icy grains. It's possible that 3I Atlas is not just carrying organic molecules, but has been synthesizing them during its long journey through space. It's a flying chemistry lab, conducting experiments over geological timescales. Now, imagine that objects like 3I Atlas occasionally collide with planets. Not Earth necessarily, but any planet with the right conditions, liquid water, and a stable environment. Each impact would be like a delivery of complex organic molecules, seeding that world with the raw materials for life. This means that life's building blocks might be distributed throughout the galaxy by these wanderers. If true, this has profound implications for the prevalence of life in the universe. It means that the emergence of life might not require each planet to independently synthesize all the necessary compounds from scratch. Instead, they're receiving care packages from the galaxy, boosting the odds that chemistry can transition to biology. Think of it like this. Starting a fire with nothing but sticks is hard, but if someone drops off matches, suddenly it becomes much easier. Interstellar objects might be the matches that allow the fire of life to ignite more readily across countless worlds. Dr. Chandra Wickramasinghe, a mathematician and astrobiologist who has spent his career advocating for panspermia alongside the late Sir Fred Hoyle, has argued in numerous papers that panspermia isn't just possible, but likely necessary to explain the rapid emergence of life on Earth. Life appears in the geological record almost as soon as Earth's surface cooled enough to support it, which is suspiciously fast if life had to evolve from simple chemicals entirely on Earth. Wickramasinghe would point to 3I Atlas as vindication of his theories, evidence that the galaxy is awash in organic chemistry that connects all planetary systems in a vast web of biological potential. Now I should note that Wickramasinghe's more extreme claims, such as that viruses and even diseases come from space, are not widely accepted by the scientific community. But his core argument about organic molecules being delivered from space is increasingly mainstream. What I want you to understand is that 3I Atlas isn't just a curiosity. It's potentially a missing link in the story of life's origins, not just on Earth, but everywhere. And that raises an even more profound question. If life's building blocks are being distributed throughout the galaxy by interstellar objects, and if those building blocks can survive for billions of years in the harsh environment of space, could life itself, meaning actual living organisms, survive such journeys? This is the question that drives the field of astrobiology and challenges our understanding of life's limits. We know that some organisms on Earth, called extremophiles, can survive conditions that would kill most life instantly. Tardigrades, those microscopic water bears, can survive the vacuum of space, extreme temperatures, high radiation, and even being completely desiccated for years, then rehydrate and continue living. Certain bacteria can form spores that remain viable for thousands or even millions of years. If such organisms were ejected into space, say by a massive asteroid impact on their home planet, blasting rocks and debris into orbit and beyond, could they survive the journey through interstellar space? Could they arrive on another planet, rehydrate in water, and start reproducing, effectively seeding that world with life? This is called lithopanspermia, the idea that life can travel through space inside rocks, protected from radiation by the rock's mass. The challenge is the timescale. Even at interstellar object velocities, traveling between star systems takes millions of years at minimum. Could any organism survive that long? Experiments on the International Space Station have shown that bacterial spores can survive years in space. But millions of years is a different story. Cosmic radiation would gradually damage DNA beyond repair. However, and here's the fascinating twist, if the rock containing the organisms is large enough, several meters across or more, the interior would be shielded from most radiation. And if those organisms are in a frozen, metabolically inactive state, time essentially doesn't pass for them. They're not aging, not using energy, just waiting in suspended animation. It's conceivable, not proven but conceivable, that life could survive such a journey. If 3I Atlas has been traveling for 2 billion years, that's far too long for any known organism to survive, even in suspended animation. But what if it's carrying organic molecules that, when they arrive on a habitable planet and dissolve in water, can assemble into living systems? That's not quite life traveling through space, but it's the next best thing. The instruction manual for life, the chemical recipes, arriving intact and ready to be executed. This blurs the line between chemistry and biology in a beautiful way. Life isn't a thing that suddenly appears. It's a process that emerges from chemistry under the right conditions. And if the galaxy is full of objects like 3I Atlas, distributing the chemical ingredients, then life might be an inevitable consequence of planetary formation, an outcome that the galaxy itself is facilitating. Let me pause here and acknowledge that we've been talking for over an hour now, and if you're still with me, I'm genuinely impressed and grateful. What we're exploring here isn't just science trivia. It's the deepest questions humanity has ever asked. Where do we come from? Are we alone? What is life? These questions have driven philosophy and religion for millennia, and now, finally, we have the tools to begin answering them empirically, with data, with observations, with objects like 3I Atlas serving as evidence in the case we're building for understanding our place in the cosmos. And every answer we find opens up 10 new questions, which is exactly as it should be. The universe is fractal in its complexity. The more you zoom in, the more detail emerges endlessly. Now, let's talk about something that might seem tangential, but connects back in a surprising way. The history of our own solar system, and what 3I Atlas might tell us about Earth's past. Our solar system is roughly 4.6 billion years old, formed from the gravitational collapse of a giant molecular cloud. The sun ignited at the center, and the remaining material formed a protoplanetary disk from which the planets, moons, asteroids, and comets coalesced. This is the standard model, and it's well supported by evidence. But there are mysteries in our solar system that this model struggles to explain. For example, Earth has an unusually large moon relative to its size, which most planetary scientists believe formed from a giant impact between the proto-Earth and a Mars-sized object called Theia about 4.5 billion years ago. The violence of this collision vaporized parts of both bodies, and the debris coalesced into the moon. This impact would have sterilized Earth if there was any life present, resetting the planet's surface to a molten state. But here's the thing. We have evidence that liquid water existed on Earth's surface as early as 4.4 billion years ago, just 100 million years after the solar system formed, from studies of ancient zircon crystals. And life appears in the geological record by at least 3.8 billion years ago, possibly earlier. That's a remarkably short window for Earth to cool, for oceans to form, for chemistry to organize into biology. It's almost too fast, which is part of what drives the panspermia hypothesis. But there's another mystery. The late heavy bombardment, a period around 4.1 to 3.8 billion years ago, when the inner solar system, including Earth, was pummeled by an intense influx of asteroids and comets. What caused this sudden mirage? The leading theory is the Nice model, named after the French city where it was developed, which proposes that the giant planets, Jupiter, Saturn, Uranus, and Neptune, formed in different orbits than they occupy today. About 4 billion years ago, gravitational interactions caused them to migrate, with Jupiter moving slightly inward and the others moving outward. This migration destabilized the asteroid belt and the Kuiper belt, flinging countless objects into the inner solar system, causing the bombardment. The model is elegant and explains a lot, but it's not without problems. The timing is uncertain, and some of the predicted consequences aren't fully observed. But here's where it gets interesting. What if some of the objects that bombarded early Earth weren't from our solar system at all? What if interstellar objects, like 3I Atlas, were part of the mix? Dr. Edward Bell Bruno at Princeton University and Dr. Amaya Morowartan, whom I mentioned earlier, have explored the possibility that interstellar objects were captured by our solar system's gravity during its early history when the Sun was part of a star cluster. Young stars form in clusters, not in isolation, and our Sun was likely born alongside hundreds or thousands of sibling stars in a dense stellar nursery. In such an environment, the gravitational interactions are complex, and objects can be exchanged between systems relatively easily. As the cluster dispersed over tens of millions of years, each star carried away not just its original planets and comets, but also captured objects from its neighbors. This means that some of the asteroids and comets in our solar system might actually be interstellar in origin, stolen from other systems billions of years ago. And conversely, objects from our system might now be part of other star systems light years away. If this is true, and evidence is mounting that it is, then 3I Atlas might be like a long-lost cousin, an object that could have been part of our solar system in some parallel history where the gravitational dice rolled differently. More provocatively, if interstellar objects contributed to the late heavy bombardment, and if those objects carried organic molecules, or even prebiotic chemistry, then Earth's life might have origins that are partially interstellar. We might be the descendants of chemistry that formed in another star system, carried here by cosmic wanderers, mixing with local materials to create the unique blend that became life on Earth. In that sense, we're not purely children of the Sun. We're children of the galaxy, our ancestry stretching back through the chemical enrichment of multiple generations of stars, across a region of space spanning hundreds of light years. This is one of those revelations that reframes everything. You look up at the night sky, and you're not just seeing distant suns. You're seeing family in a very real chemical and physical sense. The atoms in your body were forged in stars, yes, but those atoms traveled, mixed, exchanged between systems, participated in the grand project of cosmic evolution that eventually led to you sitting here watching this video. 3I Atlas is a reminder of that deep connection, that we are not isolated on an island in space, but part of a vast, interconnected web where matter and energy and information flow across the galaxy, weaving the tapestry of existence. Now, let's get into some of the more speculative, but scientifically grounded theories about what 3I Atlas might represent. I mentioned earlier the artificial hypothesis, and while it's a minority view, it's worth exploring seriously because the implications are so profound. Suppose, just for the sake of argument, that an advanced civilization existed somewhere in the galaxy 2 billion years ago. This civilization, for reasons we could only imagine, decided to send objects into interstellar space. Maybe they were probes designed to study the galaxy. Maybe they were time capsules meant to preserve information about their civilization. Or maybe they were seeds, von Neumann probes designed to travel to other star systems, use local materials to replicate themselves, and continue spreading. This is a concept that's been explored extensively in theoretical work by scientists like Dr. Frank Tipler and Dr. John von Neumann himself. The idea is that even a civilization without faster-than-light travel could, given enough time, spread across the entire galaxy using self-replicating probes. Each probe reaches a star system, mines asteroids for raw materials, builds copies of itself, and sends them to nearby stars, exponentially expanding. Calculations show that even at modest interstellar velocities, the galaxy could be saturated with such probes in just a few million years, a blink of an eye in cosmic terms. So where are they? Why don't we see evidence of such probes in our solar system? This is another facet of the Fermi paradox. Possible answers. Maybe they're there, but we haven't recognized them. Maybe civilizations don't actually do this because it's economically or ethically undesirable. Or maybe we're among the first civilizations to arise, so there haven't been predecessors to send probes. But if 3I Atlas were such a probe, 2 billion years old, what would we expect to see? First, it would need to be made of durable materials, things that don't degrade easily over geological timescales. Metals, ceramics, possibly exotic materials we're not familiar with. Second, it would need to be inactive to conserve energy, essentially dormant, until it encounters something of interest, like a star system with planets, or even technological signatures from a civilization. Third, it would be camouflaged, either intentionally to avoid detection by potentially hostile civilizations, or simply because there's no reason to make it obvious. It would look like a rock or a comet to casual observation. And fourth, its trajectory wouldn't necessarily point back to its origin, because after 2 billion years of galactic motion and gravitational perturbations from passing stars, any trail would be erased. Now, here's the uncomfortable realization. 3I Atlas fits all of those criteria. It looks like a comet, but has anomalous properties. Its trajectory has been traveling for an immense time. Its chemistry suggests a complex, possibly layered structure. Its acceleration is unexplained by simple outgassing. None of this proves it's artificial, not even close. But it's consistent with the hypothesis, which means we can't rule it out based on the available data. What would it take to confirm such a hypothesis? We'd need to get much closer, ideally send a spacecraft to rendezvous with it, study its surface and interior with instruments that can distinguish natural from artificial structures. But as I mentioned, 3I Atlas is already too far and too fast for any mission we could launch with current technology to catch it in a reasonable time frame. There is, however, a silver lining. This won't be the last interstellar object we detect. Now that we know they exist and we're actively looking for them, we're finding them more frequently. The upcoming Vera C. Rubin Observatory, also known as LSST, the Legacy Survey of Space and Time, is set to begin operations in 2025, and it will revolutionize asteroid and comet detection. It will scan the entire visible sky every few nights, detecting millions of transient events and moving objects. Estimates suggest it might detect dozens or even hundreds of interstellar objects over its operational lifetime. Some of those will be detected early enough in their approach to the inner solar system that we could conceivably launch a rapid intercept mission.